Hello everyone, this is Chandi Moinage from Cybernet Systems. We are going to look at how Ansys HFSS can be used to optimize millimeter wave array antenna design efficiency for 5G. This is a comprehensive session covering every element of the process, including multiphysics coupled simulation to do thermal analysis. So stay with us till the end. As usual, let me briefly introduce our group company for the benefit of everyone who might have joined with us for the first time. Cybernet Malaysia is a fully owned subsidiary of Cybernet Systems Company Limited, headquartered in Tokyo, Japan, established 37 years ago in 1985. Our partnership with Ansys also has a very long history. We have two other sales subsidiaries in China and Taiwan as well. You may have heard about Sigmetrix, MapleSoft, and Noises Solutions. They are also actually a part of the Cybernet group. Cybernet Systems Malaysia is a channel partner of Ansys for the countries in the ASEAN region. We are specialized in CAE, but we also provide solutions for digital transformation, such as AR applications for manufacturing and industrial IoT solutions, including engineering services, training, and consultation services in all of these domains. This presentation was originally created by our engineers at Cybernet Systems Japan. Ansys software that is referred to in this presentation are mainly HFSS, and IcePack is also used for multiphysics coupled simulation for thermal analysis. There is a white paper published by Ansys about the same topic what we plan to discuss today. Now, I think this is a really good material for additional reading. You can download it from our LinkedIn page or simply send a request by email to us so we can send it to you directly. Our email address is information@cybernet.asia. Let's dive into the main topic for today. This is just an overview of what we are going to show you today. Firstly, a bit of a background about 5G related to our main topic of the day and the challenges we face. We will discuss design issues and solutions for array antennas, which will be a key technology in the 5G era. We plan to present a design and optimization solution for array antennas using Ansys HFSS. We are going to take a 5G base station array antenna as the main example. Wireless communication technologies such as 5G and now we are even talking about 6G and the advanced driver assistance systems or ADAS technologies are visibly evolving, and the development work is going at an accelerated pace. In particular, the antennas that support these technologies are one of the most important elements. Therefore, the efficiency and precision in design and development is highly important. For example, 28 GHz frequency band is being widely tested and used in next generation 5G mobile communication systems, which is higher than the existing frequency bands, and the radio wave attenuation is going to be more pronounced than ever. These attenuations can be effectively managed by using beamforming with massive MIMO systems, which is formed by a large number of antenna elements. Also, ADAS, which is at the center of attention in the auto industry, is realized by using a wide variety of radars and sensors. For example, as shown here, a millimeter wave radar in the 77 GHz band is mounted inside the bumper of a car, and like 5G, it uses an array antenna with multiple antenna elements. All these applications are using very high frequency millimeter wave bands. Effective use of simulation is important to reduce the development cost of millimeter wave antenna arrays. However, since the design targets cover a wide range from antenna elements to system evaluation and thermal analysis, there are many issues to be addressed. There are several things to be considered when simulating these systems. The first is modeling of antennas. The increased number of antenna elements and the complexity of the radome and bumper structure, as well as the large number of design parameters, can be problematic and require more efficient modeling. Secondly, the application of high-frequency bands increases the electrical size for the analyzed structure and the number of analysis measures. Therefore, fast analysis time is essential. The third one is the radio propagation environment. The actual radio wave emitted from the antenna varies depending on the surrounding structures, and it is important to evaluate the system taking into account the actual operational environment, including the effects of multipath and built-in shadows. Another point is multiphysics. As the applied frequency increases, the temperature of the device also rises due to increased RF losses. Therefore, heat dissipation measures are important. To solve this problem, Ansys multiphysics simulation becomes quite essential. It can seamlessly perform electromagnetic and thermal analysis. Ansys HFSS enables effective design and development of array antennas for 5G and ADAS by computer simulation. Ansys HFSS can be used for a wide range of array antenna applications, including cellular base stations and terminals, radar for ADAS, and heat dissipation coupled analysis. In this webinar, we will introduce a case study of millimeter wave array antenna design using Ansys HFSS. Moving on to the analysis case study, first we will look at the overview of the design process for 5G base station array antennas. This slide shows the scope of application of electromagnetic simulation with Ansys HFSS. Ansys HFSS enables 3D electromagnetic field analysis and system evaluation from the level of small electrical components to radio propagation. Ansys HFSS is also characterized by the ability to change the analysis solver according to the scale of the analysis, thereby improving the efficiency of the analysis. During this webinar, we are going to discuss the Ansys HFSS design process for array antennas using a 4x4 antenna configuration operating in the 28 GHz band. Specifically, antenna element design using unit cells, array antenna design, power feed circuit design, performance evaluation of antenna installation, system design, and finally multiphysics, which is a coupled simulation of electromagnetic field analysis and heat transfer analysis. Let's look at each design item in a little bit more detail. First, we will discuss about the analysis of unit cell and array structures. A paced array antenna is an antenna where multiple antenna elements are arranged so that electronic scanning of the antenna beam pattern can be controlled by controlling the amplitude and pace of the feed voltage. The parameters that affect this beam pattern are mainly the amplitude and pace with respect to the antenna elements and the electromagnetic coupling between the antenna elements. These factors also change the radiation pattern and input impedance of each antenna element, which has a significant impact on the antenna characteristics. Therefore, when designing array antennas, it's necessary to evaluate the entire frequency band which is going to be used. This table summarizes the features of the array antenna analysis methods applicable to Ansys HFSS. The most general and simple analysis method is the explicit method. The full array antenna is analyzed as the way it is, providing greater flexibility in modeling and setting analysis parameters, but at a higher computational cost. Since general array antennas often use antenna elements of the same shape, unit cell design can significantly reduce computational cost while improving design efficiency at the same time. The analysis of array antennas using Ansys HFSS unit cells can be divided into two main methods, infinite array and finite array. Infinite array is an analysis method that assumes an infinite number of unit cells which are excited at a uniform magnitude without considering the radiation pattern at the edge of the array antenna. Finite array also takes into account the effects of edge and inter-element coupling of array antennas and allows the use of tapered amplitudes. The 3D component array is a further extension of these two antenna array analysis capabilities, which allows for more efficient modeling and analysis while maintaining the low computational cost of the infinite and finite arrays. This is actually an excellent feature. Let's discuss a little bit more about 3D component arrays. The 3D component array allows the entire array to be modeled in a single unit cell. That saves a lot of time. Using domain dispersion and iterative arithmetic methods, models similar to full arrays can be computed efficiently using the finite element method, reducing analysis time and memory usage. The beam pattern characteristics of array antennas can be verified in post-processing, but Ansys HFSS supports a finite array beam angle calculator that allows you to set the desired beam scanning angles, and it automatically sets the pace speed required to achieve them. This feature improves the efficiency of beam scanning verification. In this slide, you can see how beam scanning is done using the finite array beam angle calculator. Next, we are going to discuss the power feed circuit design. The power feed circuit of the antenna array is designed by a coupled analysis of electromagnetic field simulation and circuit simulation using the dynamic link function of Ansys HFSS. What you see here is an overview of the power feed circuit design and beam pattern evaluation using the dynamic link feature. When an array antenna radiates as a beam, electromagnetic coupling occurs between adjacent elements, and the excitation conditions are different in ideal conditions and in actual operation. To address this issue and to enable more accurate power feed circuit design, we can use a function called push excitation that sets excitation conditions for electromagnetic field models considering actual operation using a circuit simulator. The next step is to evaluate the performance of the installed antennas. The performance of the array antennas described so far was analyzed under ideal conditions. However, antenna performance can change when they are finally implemented in the real environment. For example, when operating a cellular phone base station, the antenna is installed on a steel tower, and the electromagnetic waves radiated from the antenna are affected by diffraction and reflection due to the shape and material of the surrounding area. The size of a base station tower is far larger than a centimeter-sized array antenna, ranging from several meters to several tens of meters, and it also several hundred times larger than the wavelength of the antenna. However, if all of these were to be included in the analysis, the simulation cost would be enormous. For this reason, it's important to select an appropriate solver to perform electromagnetic field analysis. We are now going to review each of the analysis solvers included in Ansys HFSS. The main FEM solver of Ansys HFSS, based on the finite element method, is an excellent solver that efficiently and flexibly generates meshes for structures with complex geometries, and it's a powerful tool for 3D electromagnetic field analysis. It also supports a variety of other solvers, including IE solvers, transient analysis solvers, and PO solvers that use optical approximations. And then we have the Ansys HFSS SPR Plus solver, which is characterized by its ability to efficiently handle large-scale antenna analysis. The Ansys HFSS SBR Plus solver applies a ray trace method that takes multiple reflections into account, and it's capable of fast analysis even for a very large analysis with electrical sizes of 1000 lambda or more, which cannot be solved using the finite element method. In addition, the ray tracing method can achieve high analysis accuracy by taking diffracted waves and creeping waves into account. Analysis targets include mounted antenna radiation patterns, couplings between antennas, radar reflection cross-sections, and also Doppler range analysis. The position of each solver and analytical model is shown here. The vertical axis is the electrical size and the horizontal axis is the complexity of the structure's geometry. FEM, which does not depend on the geometry of the analyzed structure, can analyze any model, but some models cannot be analyzed depending on computational resources, and some cannot be solved, especially when the electrical size is large. However, the Ansys SPR Plus solver can efficiently solve structures with very large electrical sizes, making it a very useful solver when analyzing array antennas in the millimeter wave band. The following shows the analysis method and beam pattern analysis results for base station antennas assuming an actual base installation. By using the results of the analysis performed earlier using the finite element method as the radiation source of the antenna and coupling it with Ansys HFSS SPR Plus, the actual antenna characteristics can be evaluated while minimizing the computational load. The results show that the main beam pattern is maintained, although the side lobe pattern changes due to the effects of reflection and diffraction caused by the electromagnetic radiation from the array antenna installation surface and from the steel tower. Next, we will discuss system evaluation in a real-world environment. In order to achieve stable wireless communication, it's important to select radio parameters to ensure minimum receiving power. Generally, in the initial design and development of wireless communication systems, link budgets are considered to calculate the propagation distance, minimum receiving power, based on transmit power, antenna gain, propagation loss, etc. Here's an example of link budget calculation. Using the antenna gain, feed loss, propagation distance, and propagation loss of the transmitting and receiving antennas, the received power can be estimated in this way. Although the link budget can be easily calculated with Freese equation, there are many factors that complicate the calculation, such as propagation loss calculation, interference from other receivers, and multiple bandwidth considerations. Ansys Emit is a simulation tool that enables easy and fast analysis of electromagnetic interference, or EMI, in complex wireless communications. System block diagrams can be easily created by combining existing propagation model equations and device models that make up the system, allowing efficient construction of analytical models. Propagation loss in Ansys Emit is calculated simply by using a propagation model formula instead of directly executing 3D electromagnetic field analysis. But when it's coupled with Ansys HFSS, system evaluation becomes more closer to the real environment. This shows a model for evaluating link margins between 5G base stations and terminals in urban environments using Ansys Emit. The purpose of the model is to evaluate how much margin is there between the signal-to-noise ratio, signal-to interference power, and noise power ratio with respect to the lowest received power. In this case study, the antenna gain is set as input information based on the results of the analysis. The terminal antenna is assumed to be an ideal monopole antenna, and a logarithmic distance or log distance model is applied for propagation loss, taking into account fading and shadowing. Interference noise power is assumed to be background noise. You can see that the results of the link margin evaluation. This analysis result allows Ansys Emit to confirm that both SNR and SINR have a sufficient margin against the set minimum receiving sensitivity. We are now moving into a very interesting step, which is called multiphysics analysis. In particular, the size of devices handling millimeter waves are very small, and in the coming 5G era, the heat dissipation is expected to become a bigger challenge. The output of the electromagnetic field analysis targeted by Ansys HFSS is the amount of RF loss which can be passed to Ansys IcePack to calculate the temperature. Ansys HFSS and Ansys IcePack are available on a common platform called AEDT, Ansys Electronics Desktop, which enables seamless coupling of electromagnetic and heat transfer analysis. What you see in this slide are the analysis results of temperature distribution of a 5G base station antenna using Ansys IcePack. The results show that the temperatures are distributed between 67 and 142 centigrade. Ansys IcePack supports typical heat dissipation components, and it can be configured very easily without modeling. These are some of the heat dissipation components supported in Ansys IcePack. What you see here is the analysis results of the temperature distribution of the 5G base station antenna after that countermeasure components is applied. The results show that the temperature distribution now ranges from 51 to 95 centigrades, which confirms the effectiveness of the heat dissipation countermeasure. So let's try to summarize what we discussed so far. Ansys HFSS is without a doubt an efficient way to design millimeter wave array antennas in the 5G era. Since the design requires to cover a wide design range from antenna elements to the system level, multiple factors make the design more difficult. Ansys HFSS supports a variety of solvers and functions which can be used in combination to overcome these challenges and enable a range of evaluations from antenna elements to system evaluation and coupled analysis for thermal simulation. Today we used a 5G base station antennas as an example, but this solution is very effective for any application where array antennas are being used, such as ADAS and terahertz communication antennas. With that, we have come to the end of today's webinar. I hope you found it helpful and interesting. We will reply to your questions after the webinar by email. If there's anyone who could not drop their questions in the chat, please send an email to information@cybernet.asia. If you have any questions about the analysis solutions that we presented today, please feel free to reach out to our team. You can call us, send an inquiry using the web form on our website www.cybernet.asia, or send an email to information@cybernet.asia. Our team will provide you with all the additional information, and they can even arrange a demonstration if you think these solutions can solve your design and simulation challenges. Please stay tuned to our social media channels and the newsletter for more details about upcoming webinar. Thank you and stay safe.